If I mix orange concentrate with water, I get a solution. As we showed in an earlier episode, this homogeneous mixture has two components, the solute and the solvent. Generally, the solvent is greater in amount than the solute. It is also common to have several different dissolved solutes in a solution. For example, seawater. The most common solvent is water, but there are also other solvents in which different kinds of substances are soluble. Medicines and drugs are generally aqueous or alcoholic solutions of physiologically active compounds. Chemical reactions often take place in solutions. Thus, we need to understand the methods of expressing the relative amounts of solute and solvent. We also need to learn the correct techniques to prepare solutions. Describing a solution as dilute or concentrated is a qualitative way of describing the concentration of a solution. Quantitatively, we define the concentration of a solution as the amount of solute dissolved in a given amount of solution, or by a specified amount of solvent. We can express solution concentration in a number of ways. Let's now look into the effect of temperature on the solubility of a gas. When water is heated, tiny bubbles form. These bubbles contain dissolved air escaping from the solution. As temperature increases, more bubbling occurs. The gas molecules acquire kinetic energy that allows them to overcome the attraction of surrounding solvent molecules. Boiled water tastes flat because it has lost dissolved air. As a general rule, the solubility of gases in water decreases as the temperature of the solution increases. What about the effect of temperature on the solubility of solids? These graphs show the solubility of some solids in water as temperature changes. There is no simple rule that helps us predict the effect of temperature on the solubility of liquids and solids. With increasing temperature, lithium carbonate decreases its solubility in water. Potassium chloride increases. And sodium chloride shows very little increase in solubility. Generally, the solubility of substances that absorb heat in dissolution increases with temperature. In contrast, the solubility of substances that release heat on dissolution decreases as temperature increases. Let's go to liquid solutions. Consider the liquids pentane and hexane. When mixed in any proportion, They form a single layer. We say that they are completely miscible in each other. Liquids that form a solution are miscible. The attractive forces between pentane molecules in pure liquid pentane are about as strong as those between pentane and hexane in a solution of pentane and hexane. A pentane molecule readily dissolves in hexane because there is no significant change in environment during the solution process. Pentane and hexane are both nonpolar molecules. Two liquids that are both nonpolar or both polar will readily dissolve in each other. Like dissolves like. Ethyl alcohol and water, both polar substances, are miscible in each other in all proportions. Carbon tetrachloride and water behave differently. They form two separate layers on mixing and are completely immiscible. When 1-butanol is slowly added to water and stirred, a homogeneous phase initially forms. As more butanol is added, the mixture forms two layers. The upper layer is 1-butanol saturated with water, and the lower layer is water saturated with 1-butanol. There is a limit to the amount of 1-butanol that will dissolve in water. Only 9.1 milliliters will dissolve in 100 ml of water. Why is sodium chloride soluble in water but insoluble in benzene and insoluble in carbon tetrachloride? Why are oil and wax insoluble in water but soluble in benzene or carbon tetrachloride? Benzene and carbon tetrachloride are suspected carcinogens. Be careful when handling them. The principle like dissolves like applies to these systems. Sodium chloride dissolves in water. Oil, benzene, and carbon tetrachloride are nonpolar. Can you predict what will happen when we mix vegetable oil with carbon tetrachloride? Vegetable oil and carbon tetrachloride are both nonpolar, and so they are miscible with each other. Hello. You saw in our last episode how various types of chemical reactions take place. Today, we will look closer into a form in which most reactions around us occur, solutions. Solutions are an integral part of life. Food and medicine are prepared in solutions. The making of cloth, housing materials, detergents, plastics, and steel all involve reactions in solutions. Key biological and chemical processes take place only in solutions. What makes solutions so indispensable to life? Let's find out after a short break. Chemists often find it convenient to express solution concentration in molarity. Molarity is the number of moles of solute dissolved in exactly 1 liter of solution. The chemicals used in the laboratory may not be 100% pure. On the label of the liquid reagents, you will find the specific gravity and percent purity listed. For solid reagents, only the percent purity is given. How do we prepare 250 milliliters of a 3-molar solution of hydrochloric acid from concentrated HCl? First, determine the mass of HCl in 250 ml of a 3-molar HCl solution. 3-molar HCl means that there are 3 moles or 109.5 grams HCl in every liter of solution. Therefore, the mass of HCl in 1/4 that volume, 250 ml, is 1/4 of that. Or 27.4 grams. If we know the percentage purity and specific gravity of the concentrated acid, we can calculate the volume of acid that contains exactly 27.4 grams HCl. Examine the label on the bottle of concentrated acid. According to this, specific gravity is 1.19. If you recall, this is numerically equal to density. Therefore, the density of the concentrated solution is also 1.19 grams per milliliter. Now, on the label of the bottle, you find that the solution is 36.9% HCl by weight. That means that for every 100 grams of concentrated solution, there are 36.9 grams of HCl. Multiply this by the density and you obtain the mass of HCl in every milliliter of concentrated acid solution. That is, every milliliter contains 0.439 grams of pure HCl. Remember, we need 27.4 grams HCl to prepare the solution. By a simple mathematical ratio, we see that there are 27.4 grams HCl in 62.4 milliliters of concentrated HCl. James will now prepare this solution. Using an ordinary graduated cylinder, pour about 150 milliliters of distilled water into a 250 milliliter volumetric flask. Add the 62.4 milliliters of concentrated acid to the water in the volumetric flask in small portions at a time. Swirl the flask after each addition. Rinse the beaker well with distilled water several times and add the rinsings to the volumetric flask. Dilute to the mark with distilled water from a wash bottle or a Pasteur pipette. Stopper the flask and mix the contents well by inverting it several times. Sometimes we have to prepare a dilute solution from a more concentrated stock solution of known concentration. Let's prepare 100 milliliters of a 2-molar solution of sulfuric acid from a stock solution with a 6-molar concentration. Recall, the molar concentration or molarity of a solution is the number of moles solute in 1 liter, 1000 milliliters, of solution. The solution is homogeneous, and multiplying molarity by a given volume in liters will give us the number of moles solute in that same volume. When a given volume V1 of a concentrated solution with a molarity M1 is diluted to a final volume V2, the number of moles of solute in both solutions is the same. We can show this through this equation. The difference between 100 milliliters and 33.3 milliliters, 66.7, is the approximate volume of water required for this dilution. When making this dilution, first put water in an amount less than you'll need in a volumetric flask. In this case, say 50 milliliters. Measure out 33.3 ml of 6 molar sulfuric acid. Pour this slowly, using small amounts at a time, into the volumetric flask. Swirl after each addition. Dilute to the mark with distilled water from a wash bottle. Shake well. We frequently measure the concentration of water pollutants in units of parts per million, read as ppm or milligrams per liter. Most of the chemical pollutants are harmful even at levels as low as a few milligrams per liter. We will sum up our discussion after a few reminders. Today, we discussed solubility. We also discussed the factors affecting solubility. Finally, we studied how to prepare and dilute solutions properly. In our next episode, we will tackle another kind of mixture, colloids. I hope you enjoyed today's discussion on solutions. This is your host, Ramon Miranda, saying good day. Is there a limit to the amount of solute that will dissolve in a given solvent? Let's find out. James Villanueva will now prepare a solution of copper sulfate in 100 milliliters of water. As long as solute continues to dissolve in the solvent, the solution is said to be unsaturated. More and more solute can be added to an unsaturated solution at a given temperature until a solubility limit or saturation point is reached. The solution is now said to be saturated. Solubility is the maximum amount of solute that can dissolve in a specified amount of solvent at a given temperature. Beyond this point, adding more solute means more undissolved solute. At 28 degrees Celsius, a maximum of 24.3 grams of copper sulfate dissolves in 100 grams of water. This is the solubility of copper sulfate in water at this temperature. In a saturated solution, equilibrium occurs between the solution and the undissolved solute. Two processes take place simultaneously. As the undissolved solute dissolves in solution, the dissolved solute crystallizes out of solution at an equal rate. Recall how we prepared a supersaturated solution of nickel sulfate in an earlier episode. First, we prepared the saturated solution of the solid in a liquid at a high temperature and cooled it, making sure to leave it undisturbed. A supersaturated solution is unstable because it contains more than the solubility limit of solute at equilibrium. Seeding the solution with a crystal of the solute results in the formation of larger crystals within a few days. The same thing happens when a plane seeds clouds in order to induce rain. Silver iodide and dry ice, solid carbon dioxide, serve as seeds or nuclei for condensing the water vapor in air. Let's consider the solubility of gases and liquids. Pressure has a pronounced effect on solubility only when one component is a gas. We can observe this in soft drinks or carbonated beverages. During carbonation, high pressure is applied to force carbon dioxide into solution. To maintain this pressure, the bottle is capped tightly. When I open this bottle, the pressure of carbon dioxide above the solution decreases suddenly. These bubbles are the dissolved carbon dioxide escaping from the solution. Quantitatively, the solubility of a gas in a given liquid at a given temperature is dictated by Henry's law. It states that the concentration of gas in solution is directly proportional to the partial pressure of the gas above the solution. Pressurized containers for whipped cream or shaving cream work on a similar principle. Opening a valve causes the dissolved gas to come out of the solution and force the liquid out as a foam. Divers experience another effect of pressure on gas solubility. Under high pressure, the solubility of the component gases in the blood increases. If a diver surfaces too quickly, the pressure above him suddenly decreases, and the dissolved gas in the blood, particularly nitrogen, escapes rapidly and forms bubbles. These bubbles could rupture or clog the capillaries, impeding blood circulation. Called the bends, this effect on divers causes extreme pain and in some cases death. To avoid this, divers must surface slowly. Divers may also use a mixture of oxygen and helium. The solubility of helium in blood is much less than that of nitrogen. The blood does not dissolve as much helium as it would nitrogen. Since less pressure builds up, decompression takes less time. We'll be back after a short break. In a supermarket or grocery, you'll probably find an amazingly wide array of thirst-quenching drinks. Some are sugarless, some are not. Some are caffeine-free, others not. But amid all this variety, what do they all have in common? These drinks are all solutions, homogeneous mixtures of various solid and liquid flavoring agents in water. And if you add carbon dioxide gas, you get a carbonated drink. We use many other materials around us in solutions. You probably have a number of your own examples in mind. The ocean itself is one giant aqueous solution of different compounds and minerals lying on the ocean floor. The air we breathe is a solution of gases. In our body, blood carries waste materials in solution form from the tissues to the excretory organs. The dissolved digestion products move through the membranes of the digestive tract into the circulatory system and then finally into the cells.